Okay, let's unpack this. We are diving into one of the most provocative questions being seriously debated not just in philosophy departments, but in physics labs and computer science centers today. Are we right now living inside a sophisticated computer simulation?
It really does sound like the setup for a high-budget sci-fi movie, doesn't it? And we have The Matrix to thank for making this a popular cultural concept for sure. But the mission of this deep dive is to look past the fiction and examine the hard sources. We've got statistical proofs, theoretical physics, and, actual empirical research looking for the signatures of code.
Absolutely. The simulation hypothesis, or SH, is far more than just a fun thought experiment. It's a profound extrapolation of our own rapid technological advancement. You see, if we, and we're a relatively young civilization on the technological scale, are approaching the capacity to create these highly realistic virtual worlds, worlds indistinguishable from our own, well, what does that imply about the nature of our reality? Our goal here is to synthesize the arguments, everything from Nick Bostrom's famous trilemma to the work being done searching for computational constraints in the cosmos.
Right, and it forces us to confront these fundamental questions about whether our reality is governed by underlying mathematical laws, as traditional physics holds,
Right.
or if those laws are themselves the product of something more rudimentary, like, say, optimized computer code. We are challenging the deepest assumption that our experienced reality is the single, unsimulated base layer of existence.
So where do we even begin with something this big?
Well, before we get into the bits and bytes, we have to recognize that the simulation hypothesis is merely the latest high-tech update to a very, very old philosophical challenge.
Right. How do we distinguish between what we see and what's really there?
Exactly. The phenomenal world, that's the world we perceive through our senses, and the noumenal world, which is the world as it truly exists, independent of our perception. The idea of a fundamentally deceptive or manipulated reality is as old as philosophy itself.
It's the ultimate skepticism, isn't it? It forces us to doubt the very ground we stand on. And our first source for this, the classic starting point, has to be Plato's cave. Imagine those prisoners, chained since birth, mistaking the flickering shadows on the wall for true reality.
Yeah.
The shadows are the only information they have access to. That's their entire world.
And if you look at that through a modern computational lens, the shadows are essentially a low-resolution rendering of a higher-order reality. The phenomenal world the prisoners experience is constrained by the cave environment. You could say the prisoners are conscious subroutines experiencing a severely constrained informational environment, and they're completely unaware that there are three-dimensional objects, light sources, and a world outside casting those shadows.
The whole environment is a closed loop, an informational prison.
It is. Then you fast forward to the 17th century, and the philosopher René Descartes,
Yeah.
he ramps up the skepticism with his evil demon hypothesis.
Right. Descartes was searching for absolute, undeniable certainty. So he posited, how do I know that an all-powerful, malicious deceiver isn't manipulating every single one of my thoughts, my memories, my sensory inputs?
That thought experiment is radical doubt in its purest form. I mean, if everything external could be a lie, your body, the chair you're sitting on, the very passage of time, what remains certain?
And the only thing he couldn't doubt was the doubting itself.
Exactly. Descartes' conclusion, the one unshakable certainty, was cogito ergo sum. I think, therefore I am. This established that consciousness itself, the act of doubting, the act of experiencing, is real. Even if the external world is a complete fabrication, the conscious observer exists.
What brings us right into the 20th century update? The brain in a vat. This concept takes the evil demon and simply replaces the supernatural entity with a team of brilliant, perhaps morally ambiguous scientists. The scientists surgically remove a brain, suspended in nutrient fluid, the vat, and stimulate its neurons with electrical signals that perfectly mimic inputs from the real world, creating a fabricated reality.
And functionally, the brain in a vat is identical to the simulation hypothesis. The physical substance changes from a wetware brain in a vat to a digital brain running on silicon hardware, but the experience of the conscious entity remains indistinguishable from base reality. And this is the crucial bridge, as David Chalmers has emphasized. Even if we are in a simulation, the simulation provides us with a mechanism, our simulated brains, that generates subjective experiences.
So our pain, our love, our scientific curiosity, they are all real experiences.
Yes, because the causal mechanisms generating them are real within the system's own rules. The SH simply puts the vat into a digital context.
So, okay, we have this long history confirming that our current experience doesn't guarantee base reality. But here's where it gets really interesting, because the SH takes this history of skepticism and converts it into a statistical prediction about our likely position in the cosmos.
This was the game changer. Nick Bostrom's 2003 paper. He formalized the skepticism using probability, arguing that if you accept two fundamental assumptions about technological development, the simulation hypothesis becomes statistically overwhelming.
Okay, what are the assumptions?
The first assumption is that the emergence of a sufficiently advanced post-human civilization is technologically inevitable, provided humanity doesn't extinguish itself first.
And a post-human civilization is one that has, what, mastered everything.
Basically, yeah. One that has achieved technological maturity mastering artificial intelligence, bioengineering, and crucial for this argument, planetary scale computing.
Okay, so that's assumption one. What's the second?
The second related assumption is that such a civilization will possess the capacity to run ancestor simulations. Vast, detailed simulations of their own historical development containing conscious beings. And, importantly, that they would choose to run many of them. If you agree that technological maturity eventually allows for this, then the statistical argument follows instantly.
Bostrom argues that if advanced civilizations can and do run countless high-fidelity ancestor simulations, then the number of simulated people, which he calls non-seen, will vastly exceed the number of real people in the base reality.
And if that ratio is huge, then the probability that you, an individual mind experiencing our reality, are in one of the simulated layers, well, it approaches one. You're overwhelmingly likely to be the most common thing.
And he distilled this into the famous trilemma. One of three possibilities must be true, assuming the technology is possible.
Right. So, possibility one. Almost all human-level technological civilizations go extinct before they reach the post-human simulation-creating stage. Bostrom labels the fraction of civilizations that survive to reach the stage as 5 polaris. In this scenario, 5 polaris is near zero.
This is the infamous great filter hypothesis that applied to this question.
Exactly. If this possibility is true, it suggests there is an enormous barrier that almost every civilization hits that prevents them from achieving the necessary computing power.
And the implications here are profound, because the filter could be behind us, or it could be ahead of us. If the filter is behind us, maybe the leap from single-celled to complex multicellular life, or surviving asteroid impacts, then we are one of the rare exceptions that made it through.
And if that's the case, we have a good chance of becoming post-human, and the statistical argument for being simulated remains strong for future generations, even if the filter thins the herd early on. However, if the filter is ahead of us, meaning the challenges we face are still large enough to extinguish nearly all advanced civilizations, say, global self-destruction via advanced weaponry, environmental collapse, uncontrolled AI, then 5 polaris is near zero.
And we are almost certainly not simulated, because simulations would be incredibly rare. But the implication is grim. Our future is almost certainly extinction.
It is. It's a cosmic bet. If we think we're not simulated, we should be genuinely terrified, because that implies the great filter is looming right in front of us.
Precisely. If you accept the possibility of post-human computing power, then the lack of simulations must mean there is a systematic, near-universal block on civilizations ever reaching that point.
Okay, so that's the scary one. Let's look at the second possibility.
Possibility 2. Advanced civilizations reach the post-human stage, but they choose not to run vast numbers of ancestor simulations. In Bostrom's notation, the average number of simulations run, $5 is near zero.
And this is where ethics, morality, or just resource allocation come into play. A civilization might develop such a high moral or legal standard that running billions of ancestor simulations, complete with all the suffering and conscious experience of simulated people, is deemed unethical.
Or they might just not be interested.
Right, they might pass laws explicitly forbidding it, or they might dedicate their resources to other things like exploring space or solving genuine base reality problems.
But I have to push back on this a little, because Bostrom seems to discount it pretty heavily. If they have planetary scale computing power, the cost of running an ancestor simulation might be negligible compared to their total resource budget. And why would every single post-human civilization across every possible alien culture and ethical framework uniformly decide against running these simulations?
That is the core difficulty with possibility 2. As Bostrom notes, the space of possibilities for post-human motivations is vast, but the ability to run simulations, especially for historical research, education, or even entertainment, seems so compelling. It's hard to imagine that zero advanced civilizations would choose this path, particularly if the computational cost is trivial.
If $5 is significantly greater than zero, even a small 5 dollars doesn't stop nailers from completely dwarfing a frail.
Exactly. Which leaves us with possibility 3.
We are almost certainly living in a simulation. Bostrom's mathematical formalism states that unless possibility 1 or 2 is true, then the probability of us being simulated is extremely high.
And this is where we have to contemplate the astronomical numbers underlying the argument. You have to consider the scale of posthuman capability. Experts like Max Tegmark have estimated that a Jupiter brain, a hypothetical computer built out of the mass of a planet and running at the speed of light, could perform approximately 10 operations per second.
That is an unimaginably huge number. I mean, if you consider the entirety of human history, simulating every single binary operation required to represent every particle interaction, every thought, every event, the estimate is what? Something like 10 to 10 binary operations?
Right. So if a single civilization can perform 10 operations per second, they could simulate all of human history, a deep ancestor simulation, in a fraction of a second.
Wow.
If they dedicate even a tiny percentage of their computational power to this task, the sheer number of simulated people across all their simulations will just dwarf the number of real people who ever lived in the base universe.
And this is why the tech extrapolation, which is championed so forcefully by someone like Elon Musk, lands with such weight. Musk constantly points out the speed of our own technological ascent. We went from primitive, pixelated games like Pong in the 1970s to photorealistic, massively multiplayer online worlds and immersive VRR within 5 decades.
If we project that rate of exponential improvement forward, just 50, 100, or 1,000 years, I mean, a blink of an eye in the cosmic time frame, our simulations will be completely indistinguishable from reality, meaning we are quickly approaching the capability that Bostrom defined as post-human.
And Musk concludes, based on that math, that it is overwhelmingly likely we are one of the countless simulated realities, not the one single, special, unsimulated base reality. He famously estimated the odds of us being in base reality are 1 in billions.
Now, there is a critical caveat that we have to keep reminding ourselves of. The entire statistical case collapses if the key assumption of substrate independence is false.
That's the philosophical Achilles heel, isn't it? Substrate independence means consciousness can be instantiated equally well on biological neurons as it can on silicon hardware, provided the underlying computational structure is the same.
But if consciousness relies on a unique physical property of organic matter, something irreducible that cannot be replicated digitally, then the simulations would contain only sophisticated philosophical zombies, entities that behave exactly like conscious beings but have no subjective experience.
Right. If the simulations don't produce conscious beings, then knowledge drops to 0, possibility 3 is invalidated, and we are forced back to possibility 1, extinction, or possibility 2, moral constraints.
That is why the mystery of consciousness remains the greatest philosophical challenge to the SH. But assuming consciousness is substrate independent for a moment, let's move on and see what happens when physicists actually start looking for the digital signatures.
Okay, so if we accept the statistical likelihood that we are simulated, the next logical step is to ask, what would the universe look like if it were in fact a computer program? This takes us into the realm of digital physics.
And digital physics fundamentally alters our view of reality. It proposes that information is not merely a description of physical reality, but the most fundamental entity underlying it. John Wheeler encapsulated this idea with the famous phrase, "it from bit."
Every it.
Every physical object, every particle, every field, every it ultimately arises from fundamental binary choices, or bits.
So instead of searching for the smallest particle, we should be searching for the fundamental unit of information. If the universe is built on information, the idea that it runs on a natural computational substrate becomes extremely plausible. And our search for fundamental physical laws becomes the search for the core computational rules, the code.
This notion gets put to the test when we try to simulate the universe ourselves. We, as nascent programmers, struggle immensely with simulating complex quantum systems, these many-body systems involving numerous interacting particles. Our sources discuss the limitations of digital quantum simulators, DQSs.
We use DQSs to try and model these dynamics, but they face a huge hurdle. Physical reality appears to be continuous in time, but digital simulations have to proceed in discrete steps. The source material notes that to precisely simulate the continuous time dynamics of a many-body quantum system, you need discrete, stroboscopic applications of local gates. If you want high fidelity over large scales, you need enormous, maybe impossible, computational resources.
Which is a major challenge for the simulators. How do you efficiently run a universe that behaves continuously if your hardware is intrinsically discrete? The answer, according to some research on DQS robustness, is that they might prioritize local accuracy over global far-field fidelity.
This is where we get a profound knowledge nugget suggesting a potential design choice baked into the universe's physics. Studies quantify the robustness of local observables, specifically the single-site, Phi-1s, and two-site, Phi-2.2, reduced simulator fidelities. They measured how closely the simulated reality matches the underlying base reality physics for local interactions.
And the finding was striking. They found that these local fidelities remained extremely robust, even when they introduced disorder into the simulation, like near quantum phase transitions moments where the system is inherently unstable and very hard to calculate.
Wait, so the simulation model they studied showed that the local fidelity, 5022, the two-site interaction, only decreased slightly to approximately 0.998, and Phi-1, the single-site measurement, remained above 0.999. Why is this significant beyond just being a technical measurement?
Because it suggests a brilliant piece of resource management. Think of it like a video game engine prioritizing the render distance around the player. The local quantities, the physics immediately surrounding the observer, are perfectly reliable. They are faithfully rendered in high fidelity to ensure the occupant, you, the player, can use them reliably to conduct experiments, distinguish quantum phases, or build technologies.
It's the universe maximizing the quality where the action is, and possibly letting the fidelity drop in areas far away or in systems that aren't actively being observed. It's a hallmark of optimization, to find that computational resources are being conserved while ensuring local, observable physics remains consistent and trustworthy.
So if our universe is running on a computer, then that computer, the substrate, must have finite limits. We should be able to detect the hardware specification of our reality. And the most direct approach is looking for the pixel size of spacetime.
Right. This involves searching for Planck scale constraints imposed by a rigid computational grid, or a lattice. Think of a lattice as the underlying coordinate system used in calculations like lattice quantum chromodynamics, where continuous spacetime is replaced by discrete points. If we're running on a lattice, we should see artifacts of that grid.
And one major area of investigation focuses on high-energy cosmic rays. The source material suggests scientists are looking for constraints imposed by a hypercubic space-time grid. There's a well-established phenomenon called the GZK cutoff.
The GZK cutoff, named after Greisen, Zetsipin, and Kuzmin, dictates that extremely high-energy cosmic rays protons traveling through space should lose energy rapidly upon colliding with photons from the cosmic microwave background. Essentially, beyond a certain energy level, around 10 electron volts, you shouldn't see any protons traveling long distances because the universe acts like a fog, sapping their energy. It's a cosmic speed limit for high-energy particles.
So researchers hypothesized that if spacetime were not a smooth, continuous medium, but rather discrete points on a lattice, that lattice spacing, which they call bidollars, would interfere with the particle interactions. To account for the observed GZK cutoff, they calculated that the lattice spacing must be incredibly tiny, less than approximately 10 or 12 femtometers.
To put that into perspective, an atom is about 10 meters wide. A proton is about 1 femtometer, 10-15 meters wide. So we're talking about a grid that is 1,000,000 times smaller than a proton, yet still many, many orders of magnitude larger than the theoretical Planck length, which is considered the absolute theoretical minimum size. This tiny yet non-zero lattice spacing would be a sign of discrete computation.
Now, here is the critical testable prediction. If the lattice spacing is responsible for the GZK cutoff, then the extremely high-energy cosmic rays traveling through this hypercubic grid should exhibit a unique signature. Instead of the angular distribution of these rays being isotropic, the same in all directions, as you'd expect in smooth spacetime, the distribution would exhibit cubic symmetry in the rest frame of the lattice.
So we'd be looking for a slight preference for particles to travel along the axis of the underlying computational grid, rather than diagonally. Finding such a cubic pattern, even a tiny, subtle deviation from perfect randomness and isotropy, would be tremendous empirical evidence that our universe is fundamentally discrete and running on a grid. It would strongly bolster the SH.
This work also highlights a theoretical benefit for the simulator. By introducing a lattice spacing much larger than the Planck scale, the simulation might bypass the intractable theoretical conflicts between quantum mechanics and gravity that plague base reality physics. It's an elegant coding solution to a deep physical problem.
Okay, so that's searching for the limits of the hardware. Now let's look at the limits of the software, specifically related to information flow. The source has introduced a pretty radical concept challenging conventional thermodynamics.
Yes, the second law of information dynamics, or infodynamics. The standard second law of thermodynamics states that physical entropy, a measure of disorder, must increase over time. The universe tends toward maximum chaos.
But infodynamics suggests the opposite is true for information entropy. Research, demonstrated in systems ranging from digital data storage to biological RNA genomes, implies that information entropy must remain constant or decrease over time. This is the universe naturally trending toward minimum information content.
Which creates an entropic paradox that has deep implications for a computational universe. Here's why. The first law of thermodynamics says total energy and entropy must be conserved in a closed system, which we assume the universe is. If the universe is adiabatically expanding, so no heat exchange with an external environment, the total entropy should be constant.
But wait, physical entropy, the disorder we observe, is constantly increasing. So if the total is constant and one component, the physical entropy, is increasing the other component, the information entropy, it must be decreasing to compensate. It's acting as an entropy sink.
Exactly. This suggests there is an unaccounted entropy term in the universe's total energy budget, and this term, information entropy, is systematically minimizing itself.
And what does this minimization of information entropy actually look like in physical reality?
It looks like symmetry. The infodynamics law implies that the fundamental symmetries we observe everywhere in nature are a consequence of the universe constantly minimizing its information state. For example, Hund's rule in chemistry dictates that when filling electron shells, electrons prefer to occupy separate orbitals with parallel spins, leading to the highest total spin quantum value. That configuration corresponds precisely to the lowest possible Shannon information entropy.
So instead of thinking of these symmetries as some kind of inherent abstract beauty, they are actually the result of the universe efficiently compressing its own code.
It's the ultimate form of data compression. The universe chooses the lowest information configuration available. If you think of the universe as a simulation, the simulators would naturally program laws that favor maximum efficiency and minimum data usage. And the second law of infodynamics might be the mathematical expression of that optimized programming.
Okay, so the statistical case is compelling, and the physics hints at optimization. But this all falls apart if the scale of computation required for a full universe simulation is just, well, impossible. These are the sim blockers, the practical reasons why even advanced civilizations might fail to run the system we inhabit.
And the first major barrier is the exponential growth of computational complexity inherent in simulating certain quantum phenomena, particularly those involving gravity. A significant study investigated the feasibility of simulating the quantum Hall effect, which is a complex phenomenon arising in two-dimensional systems where electrons are subjected to low temperatures and strong magnetic fields.
And the finding was that simulating this specific quantum behavior, especially when it involves gravitational anomalies, causes the computational complexity to grow exponentially with the number of particles involved.
That is the death knell for a simulation. If you double the size of the simulated system, the number of particles, the computing power needed doesn't just double, it might quadruple or even increase by a power of 10. To simulate a universe containing $10 particles down to the level of quantum interactions, especially those tied to gravity, the required computational resources quickly become astronomical and physically impossible, even for a Jupiter brain.
But wait, doesn't that directly contradict the idea that the simulators are using resource management, like the local fidelity optimization we just discussed? If they can simplify the rendering for distant objects, why would they need to track every single quantum interaction for the whole universe?
That's a critical pushback. Proponents of the SH argue that the simulators don't track everything. They only track what is necessary to maintain local consistency for the conscious occupants. However, the sim blocker argument suggests that for certain specific foundational physics, like the relationship between quantum mechanics and gravity, the entire system is so deeply interdependent that you cannot simplify or cut corners without the whole simulation immediately diverging into incoherence. If you can't simplify gravity and quantum interaction, the simulation is intractable.
That brings us to the second sim blocker, computational irreducibility, CI, put forward forcefully by thinkers like Stephen Wolfram. This principle posits that some calculations cannot be sped up. The complexity is such that the only way to determine the outcome is to run the calculation itself in real time or slower.
And CI fundamentally undermines the primary motive for running ancestor simulations. If the purpose of the simulation is to predict the future state of reality, for instance, to forecast the outcome of a complex historical contingency, or to understand chaotic phenomena like when a star will become a supernova, and that simulation takes longer than the actual physical process, it loses all predictive utility.
If the only way to find out what happens is to watch it unfold, why bother simulating it billions of times? This significantly reduces the likelihood that advanced beings would bother running vast numbers of these time-consuming simulations, which reduces $5 to near zero and directly challenges Bostrom's possibility 3.
It turns Bostrom's statistical argument right on its head. If computational irreducibility is a universal law, it suggests that complex universes like ours are inherently unsimulatable on a massive scale for predictive purposes, which means the base reality is likely the only reality.
So the question shifts from, can they build a big enough computer, to can they write the code any faster than reality runs itself? If the answer is no, then nuz is small and we are probably real. This conflict between statistical likelihood and computational viability is really the heart of the modern debate.
Now, if the universe is indeed a massive computational program trying to conserve resources, as suggested by the infodynamics law and the DQS fidelity studies, then the strangeness of quantum mechanics might not be some inherent universal mystery, but rather incredibly efficient code optimization.
This is the idea that the simulation only bothers to render what is absolutely necessary for the occupant to perceive or interact with. It's the ultimate case of selective fidelity.
Let's fully lean into the video game engine analogy here. Imagine a massive open-world game. The game engine cannot, at all times, track the position, velocity, and lighting of every single pebble and leaf across the entire simulated planet. That would instantly crash the system.
So what does the game engine do? It uses level of detail optimization, or LOD. A distant building is initially just a few low-resolution pixels. It exists only as a potential set of information. It only resolves into high-definition textures and geometry when the player approaches it, forcing the system to render the details for immediate observation.
Quantum mechanics behaves exactly like this. Before a measurement or interaction, a particle exists as a probability wave, an unrendered possibility set, a cloud of potential states. It's not in a definite position or spin state.
It's only when a measurement occurs, the player approaching the building, the interaction extracting information from the system, that the wave function collapses it into a single definite state, a specific location, a specific spin. The simulation doesn't waste computational cycles calculating the definite state of every single particle in the cosmos. It only renders what is forced to be observed.
And this resource management approach elegantly explains the famous observer effect. It's not that consciousness is required, but that the interaction necessary to extract information forces the system to finalize the particle state.
Here is where the code gets truly weird, though, because it seems to break its own internal rules to maintain consistency, which is a classic feature of buggy or over-optimized code. Let's talk about delayed choice experiments.
These experiments, derived from the double-slit setup, demonstrate a form of retrocausality. In some versions, the decision to observe the particle or not is made after the particle has passed through the apparatus. Yet that later decision still determines the particle's behavior backward in time, changing its past state to ensure consistency with the present observation.
Think about that computationally. If a particle 100 million light-years away passes a cosmic lensing event, and we only observe it now, the measurement must instantaneously collapse the wave function all the way back to the source 100 million years ago, ensuring that particle's historical path is consistent with the current measurement outcome.
That is the simulation's underlying programming, ignoring the fundamental constraint of speed limits imposed by the constant speed of light. The speed of light is a great optimization rule for internal operations. Preventing information from crossing the simulation faster than some tau keeps things orderly and predictable for the occupants. But the simulator itself can bypass this rule when necessary to prevent glitches in the historical record.
Which brings us to quantum entanglement. Einstein called it spooky action at a distance because two entangled particles share an instantaneous connection regardless of the vast physical distance separating them.
Right. If you measure the spin of particle A, you instantly know the spin of particle B, even if it is across the galaxy. This instantaneous information transfer appears to violate the speed of light limit. For a non-simulated physical universe, this is a deep mystery. But if the universe is a program, entanglement is simply two memory registers being linked by the base code. The underlying program bypasses the in-simulation rule of two Othalers because the two particles are just referencing the same memory block in the core simulation code, allowing for instantaneous state updates.
Okay, beyond these strained efficiencies, some scientists have looked for literal textual evidence, the equivalent of finding a comment in the code that says, "This is a simulation."
And the most famous proponent here is physicist Jim Gates, known for his work on supersymmetry and string theory. He discovered that the mathematical equations describing fundamental particles and their interactions contain strange, complex structures that look exactly like error-correcting codes.
And error-correcting codes are essential in digital systems. They are redundant data added to a message that allows the receiver to detect and correct errors introduced during transmission or storage. Finding this type of code embedded directly into the foundational equations of physics, which are supposed to describe nature, not computation, is extraordinarily suggestive.
Gates noted that finding this specific type of code in a non-computed base reality universe would be extremely unlikely. The very regularity, stability, and consistency of physics, the fact that we don't wake up tomorrow and gravity is suddenly 3 times stronger, might not be a sign of universal law, but a sign of a highly advanced error correction system running constantly in the background, preventing fundamental glitches.
Then there's the profound mystery of dark matter. We know it exists because we can measure its gravitational influence, but it's transparent. It doesn't interact with light, and we don't know what it's made of. It is 6 times more abundant than regular visible matter.
In a debate, the analogy was raised that dark matter acts like the operating system of the universe. We can't form galaxies without it. Its gravitational presence is what creates the massive gravitational wombs required for regular matter stars, planets, us to collect and begin forming structures.
So why would a simulator include 6 times more material that is invisible and seems superfluous, thereby dramatically increasing the CPU cost of the simulation?
The argument from people like Max Tegmark is that everything we've discovered in the universe that seems superfluous, like the finely tuned constants of physics or seemingly extra matter, has eventually been found to be essential for our existence.
Dark matter, despite the computational expense, is essential for generating galaxies, which are essential for generating observers like us. If the goal of the simulation is to produce conscious observers capable of research, then the dark matter operating system is a necessary, albeit costly, component.
And this leads directly into the file signature. Symmetry breaking. The fundamental high-energy laws of physics are beautifully symmetric. They treat matter and antimatter equally and operate identically under spatial reflection or time reversal.
But if those symmetries held exactly, the universe would only contain photons and would be entirely devoid of complex structures. For atoms, chemistry, and eventually life us to exist, those fundamental symmetries had to be broken in the early universe, allowing matter to slightly dominate antimatter, for example.
The necessary breaking of symmetries is a profound mystery. It suggests that the universe's current state is not accidental or purely mathematical, but perhaps intentional. The simulation, if it exists, had to break those elegant symmetric laws deliberately, like flipping a series of switches, to ensure the universe reached the interesting, complex phase containing self-aware observers. It looks like a carefully designed boot sequence.
We circled back to it earlier, but we have to directly confront the greatest vulnerability of the simulation hypothesis, the nature of consciousness. As we established, the entire mathematical structure of Bostrom's argument relies on the premise that consciousness is substrate independent.
If the complex structures of consciousness rely solely on the computational architecture, the organization of the processes, and not on the material, the substrate, running them, then a digital brain is as good as a biological one. But how do we know this is true?
Well, as Max Tegmark admitted, consciousness is the biggest embarrassment in fundamental physics. We are, to use his term, clueless about how to describe subjective experience mathematically.
Philosophers, notably David Chalmers, distinguish between the easy problems and the hard problem of consciousness. The easy problems are the empirical correlates, describing the neural pathways, mapping brain activity, describing how inputs lead to outputs, and describing the function of behavior. These are difficult, but solvable through standard scientific inquiry.
The hard problem, however, is the irreducible nature of subjective experience, or qualia. Why does the processing of sensory information feel like something? Why is the experience of seeing the color blue fundamentally different from seeing the color red? This raw internal feeling remains completely unexplained by our current physical laws.
If consciousness is a truly fundamental non-computational property of reality like space, time, or mass, then it may not be replicable in a digital format. If that's the case, possibility 3 dies instantly because the simulations contain no one to observe them.
This makes the scientific progress on consciousness the ultimate test for the SH. Tegmark argues that if we, the inhabitants of this universe, succeed in providing an exhaustive, reductive mathematical description of consciousness that completely explains subjective experience, it would be the biggest boost possible for the simulation hypothesis.
It would validate the view that reality is purely mathematical and computational, and that consciousness is simply the output of a specific, elegant algorithm. Conversely, if, despite decades of effort, we remain utterly clueless about the hard problem, it strongly suggests the universe is not purely mathematical computational, dealing a serious, if not fatal, blow to the simulation idea.
It seems like the best way to prove we are real is to fail to solve our own minds.
So let's assume the statistical case holds and consciousness is substrate independent. We must now turn to the ethical and existential implications. If a simulator exists, what is their intent?
One optimistic line of reasoning suggests that any civilization that successfully navigates the great filters, avoiding self-destruction from technological risks, global conflicts, and coordination failures, is likely to be highly ethical. They would have had to embed restraint, cooperation, and long-term stability into their societal structure just to survive to the post-human stage.
Therefore, the simulators are likely not malevolent or whimsical. The only rationales proposed as being robust and structurally stable enough to justify running conscious simulations are education and problem solving. They might run ancestor simulations to explore historical counterfactuals. What if we chose an option A instead of option B? Or to prepare their own civilization for threats they haven't encountered yet.
And this assumption about ethical simulators yields expected design signatures in our physics and history. The selective fidelity we discussed, sparse rendering in the background, high detail only in moments of decision or crisis, makes sense if the goal is data acquisition about consciousness and historical outcomes, not perfect replication of every leaf.
Furthermore, we might expect pruning. If the purpose is research, there is no need to let a simulation run its course if it enters a low-yield state, such as nuclear war or total self-destruction. The fact that humanity has repeatedly skirted existential annihilation surviving the Cold War, avoiding catastrophic bioweapons use, could be interpreted as weak Bayesian evidence that low-yield branches are pruned or delicately nudged by the simulators to keep the data stream interesting and informative.
That thought is chilling. We might not be lucky. We might just be gently steered back onto the path of interesting data.
Finally, what are the existential implications for us, the simulated occupants? This immediately raises the ancient debate over free will. If our reality is a deterministic program running on a supercomputer, is our experience of choice merely a complex, pre-programmed delusion?
If the base reality is deterministic, then our simulation is certainly deterministic, and the entire history of the universe was written the moment the program was booted up. However, even if systems are fundamentally deterministic, complexity can lead to such chaos and unpredictability that the system is only pseudo-random. For all practical purposes, our choices appear free, even if they are fundamentally traceable back to lines of code.
David Chalmers, the philosopher who popularized the hard problem of consciousness, argues that living in a simulation should not change how we live. His point is crucial. The simulation is a genuine reality. The value we place on relationships, experiences, and projects comes from the subjective experience of those things, which, assuming substrate independence, are perfectly real and valuable when in the system.
So if your pain is real, your love is real, and your discoveries are real, who cares if the structure supporting them is atoms or bits? The value is intrinsic to the experience.
However, others speculate on the behavioral implications. Robin Hanson introduced the concept of the simulator's gaze. If you become convinced you are simulated, your incentives change.
Instead of caring about long-term goals like saving for retirement or reducing carbon emissions, systems which might be terminated arbitrarily when the simulation ends, you might focus instead on behavior that is entertaining, moral, or praiseworthy to the simulators.
You might actively strive to be interesting or good in the hopes that the simulators will promote you to a higher fidelity simulation, or perhaps simply keep your branch of the code running rather than terminating your existence or shifting you into a low-fidelity, non-conscious part of the simulation when your data yield declines. It changes your entire incentive structure from pleasing humanity to pleasing the external programmers.
The ultimate existential question then becomes, what do they value? And how do we perform for the audience we can never see? So what does this all mean? We've taken the deepest dive possible into the question of whether our universe is code. The simulation hypothesis is supported by powerful statistical arguments. If post-human civilizations exist and run simulations, the math says we're probably simulated.
We also found compelling hints of computational efficiencies embedded in the fundamental rules of physics. The highly robust local fidelity of quantum observables, the implications of infodynamics pushing the universe towards optimized information states, and the strange resource management techniques inherent in wave function collapse and entanglement.
But the hypothesis is not without powerful challenges. The sim blockers. The exponential computational cost of simulating phenomena like the quantum Hall effect and the concept of computational irreducibility suggests that running a universe this complex may be physically impossible, thus undermining the entire statistical premise.
And of course, the enduring philosophical challenge of consciousness remains. Until we can definitively solve the hard problem, the foundation of the SH rests on a shaky assumption that the subjective feeling of existence is something that can be purely digitized.
But what's truly exciting is that this isn't just philosophy anymore. Scientists are actively searching for empirical proof. The work on finding rotational symmetry deviations in the highest energy cosmic ray spectrum, looking for that telltale cubic pattern, and the search for error-correcting codes in fundamental equations are genuine, active research programs attempting to turn this speculation into testable physics.
Ultimately, our capacity to investigate the simulation is constrained by the laws of this universe. We are running code on the machine, trying to reverse engineer the operating system, and we may be limited by the speed and complexity of the OS itself.
That brings us to our final provocative thought for you to chew on. The history of science is filled with moments where overwhelming complexity dissolved into hidden, unexpected simplicity. Think of Newton finding one law for the apple and the moon, or Einstein unifying space and time. Could the ultimate act of scientific discovery be figuring out the computational rules of the game and potentially finding the one simple, elegant equation the simulator wrote down to create our entire vast universe? Because if we find that equation, we will not only have confirmed our reality is digital, but we will have fully figured out the code of creation itself.